Welcome. This video is covering equilibrium part 2. In an earlier video, we introduced the idea of equilibrium and what it is. And in this video, we are going to look at how to write the equilibrium expression, how to calculate the value of the equilibrium constant and interpret the magnitude of that, and then looking at writing Kp versus Kc expressions. And if you want to follow along in the TRO textbook, these are all in the first few sections of chapter 14 in TRO. So a little review about equilibrium and relating this to kinetics. So we know that a system is at equilibrium if the rate of the forward reaction is equal to the rate of the reverse reaction. And we know that for an elementary step in kinetics, we can write the rate law for a step, and the rate is going to be proportional to the concentration of the reactants to this exponent we call the reaction order. And for an elementary step, the reaction order is going to equal the coefficient there. And so we can say the rate forward is A to the power of A. And then for the reverse reaction, we can think of B as being the reactants in the reverse reaction. So the rate of the reverse reaction is going to be proportional to the concentration of B to the power of B. And then at equilibrium, the rate forward is equal to the rate reverse. So A to the A is B to the B, and then we can rearrange it and solve for some constant K. And we see that K is a ratio of the products to the power of their coefficient over reactants to the power of their coefficient. So this is the derivation of what we call the equilibrium constant. So I'm just trying to show you how this relates to the kinetics background to equilibrium here. And then this is what we call the equilibrium constant. And we use the symbol K for the equilibrium constant. Notice that here it is a capital K. That distinguishes it from the lowercase k, which is the rate constant. We seem to like using K as a symbol for a constant. So lowercase k is the rate constant. Uppercase K is the equilibrium constant. This right here is something called an equilibrium expression here. And if we look at this equilibrium expression, notice that K is equal to the products raised to the power of their coefficients divided by the reactants raised to the power of their coefficients. This is what we call a Kc expression, which means that the amounts of the products and reactants are going to be given in a concentration. So C is for concentration. And remember, whenever we see square brackets, that implies that we're talking about the concentration of A or the concentration of D right here. And we measure concentration in molarity. So just FYI, in a Kc expression, we're going to express the relative amounts of reactants and products in terms of molarity. That's what the square brackets represent. Sometimes we will be interested in the Kp for a reaction. So notice that this K expression, the similarities to the previous one is it's still products over reactants, and the coefficients become the exponents. But the difference here is the symbols that we use. So instead of using square brackets, which represent molarity, we are using this symbol right here. And what this stands for, if you say like P sub A, that means the partial pressure of A. And when we give a Kp value, or if we try to calculate the value of Kp, we need to make sure that the pressures are being measured in atmospheres. And that's just basically how we define the Kp is we take the partial pressures of those gases in atmospheres and plug them into the K expression. So this can work if you have a system involving gases. So you want to be able to write a Kp expression or a Kc expression. Make sure we're using the appropriate symbols there. And another interesting thing about the K expression is that we do not include pure solids or pure liquids. So we say that it's, the K expression is products over reactants, coefficients become exponents, just like we were showing right here. But if one of these things is a solid or a liquid, it gets left out of the K expression. And that's because the concentration of a solid or a liquid does not change during a reaction. So if someone asks you, what's the concentration of water? You'd say, well, that's a weird question, right? And the concentration of water is not going to change throughout a reaction. So we leave those out of the K expression. And so that means as a result, we only include solutions or gases. So if you see an A, Q, or a G by it, include it in the K expression. If you see an S or L by it, leave it out. And then we're going to look at some examples of writing these K expressions. So if we're to write the KC expression for these ones, whoops. So the KC expression, it's going to be products over reactants. So my products are HCO3 minus, the bicarbonate ion, and I'm going to put square brackets around it. So that means concentration of bicarbonate. And then my other product is hydroxide ion. And the coefficients are 1, so they're both to the power of 1. We typically just don't write the 1. Okay, and then on the bottom, our reactants are the carbonate ion and water. But water is a liquid, so we leave liquids out of our K expression. So this right here is the K expression for this reaction. All right, now let's write it for the second one. So down here, again, we're going to write a K expression. It's a KC expression. So we're going to use the brackets to represent concentration. So our products are silver ions, but in this case, it's got a coefficient of 2. So what that means, I'm going to square the concentration of silver. So the coefficient becomes the exponent in these K expressions. And then sulfate over here, and these are both aqueous, so they get included in the K expression. And then this one over here, our reactant is a solid, so it does not get included in the K expression. So there's nothing on the bottom. You could write divided by 1, or you could just kind of leave that out. And so this is the K expression for this reaction. So we leave out solids and liquids, products are over reactants, and then coefficients become the exponents. All right, here's one more. This one we're going to write the Kp expression, Kp. And so the symbol we would use is we would say the pressure of, and let's take a look at the states of matter. Notice we have 2 things that are solids and only 1 gas. So we leave out these solids. So the only gas we have, gas or aqueous, is oxygen. So it's the pressure of oxygen cubed. And that's it. There's no denominator because the reactant is a solid. So there you go. So you might end up with an expression like this where there's no denominator. If we reverse this reaction, let's do that example real quick actually. If we were to reverse it, in case you're wondering what that would look like, it would look like this. So if the product was a solid, you just write a 1 there, and then you would put the reactant on the bottom. So wherever you see a solid or a liquid, you could think of replacing that with a 1. That's another helpful way of thinking about it. All right. The units of K. Something that's nice about the equilibrium constant K is that the K values are unitless by definition. But here's where you have to be careful about the equilibrium constant K versus the rate constant K. So just as a little side note here, reminder, the rate constant, which is the lowercase k, does have units. Remember we saw lots of questions about finding the units of the rate constant K, like sometimes you see things like this, 1 over molarity second. So the rate constant does have units, but the equilibrium constant does not have units. Why is that? It's just by definition. It's the way that the rate constant is defined, is that the values you are putting into the K expression to solve for the value of K are actual ratios. And we don't need to get into the details here right now, but just so you know, as a result of this, the K values are always unitless, okay? And then we're going to take a look at some examples of how things reach equilibrium here. So taking a look at this reaction, this is an equilibrium system where we have 1 molecule of N2O4 that's forming 2 molecules of NO2. If we were to write the K expression for this reaction, let's write the Kc expression, it would be NO2 squared over N2O4. And we can take a look at various different scenarios here. So here's a scenario where we start with pure NO2. So we start with pure product. And now some of the NO2 turns into the reactant. Remember, this reaction's reversible, so it's really arbitrary who we're calling the reactant or product. So we could start with pure product, we could start with pure reactant. Okay. So here we're starting with pure product, and notice how at some point we're going to reach equilibrium. So the amount of reactants and products stop changing. This scenario, we start with pure reactants. Again, we reach equilibrium, but notice how the equilibrium position is different than it was over here. But in both cases, the amount of N2O4 was greater than the amount of NO2. And then here's a third scenario where we start with some NO2 and some N2O4. And again, they'll reach equilibrium, but the equilibrium amounts are different. So different equilibrium positions each time. And then here's this information in a data table form. So you'll notice that at equilibrium, in all these various trials, the amounts of reactants and products tends to differ here. So this part is not constant. But if you were to plug these values in to that K expression we just wrote, and if you took the NO2 squared divided by N2O4, you would see that they have the same value, that value is the same no matter what your initial setup is. That's why we call this the equilibrium constant. So like for this reaction, if we take the product squared divided by the reactants, we will end up with the same value when these reactions reach equilibrium, no matter what we're starting with. No matter if we're starting with all reactant, all product, some mixture, that ratio of product squared divided by reactants will always be constant. Hence the idea of the equilibrium constant. And notice that in this case, the constant here is less than 1. Right, it's 10 to the negative 3, so K is less than 1. And if you think about what that tells us is the ratio of products to reactants is less than 1, which means you end up with more reactants than products at equilibrium. And let's go back and double check that. Yep, we have more reactants than products at equilibrium. So you have more N2O4 than NO2. All right, so there's some different K symbols that we will learn. So we will find that KEQ, this is the generic form. KEQ just means equilibrium constant. But we use different subscripts depending upon which type of K expression we're looking at. So if you have a KC, means you're using concentrations and molarity. KP is you're using the partial pressures of gases. And then there are some various types of KC expressions that we will see down the line here. And I just want to introduce those to you now, so as you see them later, you realize that these are all the same thing. These are all just K expressions. We just use different subscripts for different scenarios here. So there's a KSP is the solubility product, and that's a K expression for something dissolving. Ka is a K expression for acids. Kb is for bases. Kw is for water. You get the idea. This is something that will be a big theme throughout the next several weeks here, is these various equilibrium systems. All right, so the magnitude of K. So we were just talking about the idea that the K value of that reaction we saw was less than 1 and what that means. So if a K value is less than 1, we say the reaction is reactants favored. And if a reaction is reactants favored, that means that equilibrium, it's going to be mainly reactants present. So that forward reaction does not really proceed very far. If the K is close to 1, then neither reaction is really favored. The forward reaction proceeds about halfway. You got about equal amounts of reactants and products. If K is greater than 1, we say the reaction is products favored, which means we make a lot of products at equilibrium. So let's take a look at some examples of what this looks like. So thinking about the magnitude of the equilibrium constant. So we've got a few visuals here. You're looking at a particle level view, and these different scenarios all show these reactions at equilibrium. And so we want to assume that if you assume the volume of the container is 1 liter and each sphere represents 0.1 moles, what's the value of K for each system? So let's take a look at this one. In this one, our products are the blue sphere and the reactants are red. And so if I look about my number of red ones, I've got 1, 2, 3, 4. So I've got 4 reds. And then my products, I've got 1, 2, 3, 4, 5, 6. I've got 6 products. Okay. So if I write the K expression, it would be products over reactants. They said to assume each of these are 0.1 mole, so I'm going to write like this. And you'll notice that we have more products than reactants. So our K value is going to be greater than 1. Here I'll go to this next slide where I've calculated this out. So in this case, our K ratio is going to be the products over reactants. In this case, it's blue over red. And we've got more blue than red. So the K value is 1.5. Over here in this second reaction, we only make 1 molecule of yellow and we still have 9 green left over. So our K, the ratio of products to reactants at equilibrium is 1 over 9. So the K value here is 0.1. And then over here, our products are red. We have 8 reds for every 2 blues. So our K value, that ratio of products to reactants, is 4. So we can see how this K value is giving us a sense of whether we have more reactants or more products. So in this third one, it's got a K value of 4. It's got a lot more products than reactants. In this scenario, the K is 0.1. So this one has a lot more reactants than products at equilibrium. So that's what that K value is giving you a sense of. Here's another example here. Looking at this scenario, is the K value greater than 1, less than 1, or equal to 1? So we have this reaction where you have these AB molecules that are decomposing and breaking apart into A plus B. So if we take a look at those, we've got a bunch of particles of AB still there. So wow, it looks like we got a lot of reactants still present and not very many products. So I'm going to look at this and it looks like my K value is going to be much less than 1 because I have mainly reactants present here in this equilibrium mixture. So different equilibriums are going to have different K values. It could be greater than 1. It could be less than 1. You want to think about what that tells you. Okay. So as a summary here, a reaction is at equilibrium when the rate of the forward reaction equals the rate of the reverse reaction. At that point, the concentrations of reactants and products stop changing. So the reaction doesn't stop, but the forward and reverse reactions go at an equal rate, so the amounts stop changing. And when you write a K expression, here's my things I always think about. It's products over reactants, coefficients become exponents, leave out pure liquids and solids. Those are your 3 things to think about with writing a K expression. If you look on your equation sheet, you will see this right here. So your equation sheet kind of gives you a hint about how to write the K expression. It gives you some pretty big hints here. So there's lots of useful information about equilibrium on your equation sheet if you want to go look at that as a reference too. Okay, and then a review about interpreting the value of K. So if K is equal to 1, you've got about equal amounts of reactants and products. If K is greater than 1, you've got more products than reactants. Okay, so by the way, connecting this back to thermo, if you have more products, that means that forward reaction is favorable. So in this case, we'll find that we have a negative delta G. So if that reaction's favorable, you're going to make a lot of products, you're going to have a K value greater than 1. We'll talk, there's actually a mathematical connection between G and K that we'll talk about in a different video. All right, if K is less than 1, that means that forward reaction's not favorable. And so therefore, you're not going to make very many products, and you're going to end up with mainly reactants in your mixture at equilibrium. Here is this as a visual, if this kind of helps you visualize what's going on. So this is the example where K is greater than 1. You can see we've got more products than reactants. This is the example where K is less than 1. We've got more reactants than products. And it's some more vocabulary here is that sometimes people say the equilibrium lies to the right in this scenario, or we might say that the equilibrium is products favored. Those are just different ways to say that you end up with more products at equilibrium. In this scenario, we call it reactants favored, or you might hear someone say that the equilibrium lies to the left. Those are just some vocabulary terms there. All right, so here's some more practice problems. So what you want to do here is you want to pause the video, try writing out these K expressions, and then when you've done it, then hit play again and you can check your answers. So right now, pause the video and try writing out the Kc expression, so C for concentration, for the following reactions. All right, so you should have paused it, and now you're checking your answers. So these are KC expressions, so you should use square brackets. Notice how it's products over reactants. The coefficients become exponents, and then we leave out pure solids or liquids. So we left out the nickel oxide and the nickel here, and then we left out the water in that last one right there. So we leave out solids and liquids. All right, here's another one where I want you to stop your video and answer the questions that you see on the screen. So I'm gonna give you a moment to pause, stop your video, and try this on your paper and your notes. All right, and now you've stopped your video and you're coming back to check your work. And let's look at this one. So write the K expression. So K expression is products over reactants. Coefficients become exponents. And then we can also calculate the value of K if we know the values of these concentrations at equilibrium. So I can plug these values into my K expression, and when I do that, I get 59. So that's my K expression. And notice how K is greater than 1. That's telling me we have relatively more products than reactants at equilibrium, which matches what we see here. Okay. All right, one more. Here's one from an old AP exam. So you can see what this looks like. I have a note here to try this without the calculator because the multiple choice questions on the AP exam are designed to be done without a calculator. So give it a try. So you're trying to find the value of the equilibrium constant. I can give you a hint. What you might want to do is write the K expression first and then plug these numbers in to solve for K. So try that, pause the video. Okay, so now you're back. I'm trusting you've paused the video and tried this problem on your own. And what you should get, the answer is E32. Okay, so you just write your K expression, then you plug in the numbers and you get 32. All right, and this is our last one. This one's just practicing interpreting the values of K. So based on what you're seeing here, would you call the following reactions reactants favored or products favored? All right, and what I'd say over here for this one, problem 7, the K value is much less than 1, so I'd say it's reactants favored. And what that means is like at equilibrium, there's going to be a lot more reactants than there are products. This one over here, K is greater than 1, so 10 to the third, that's about 1,000. So that means it's products favored, which means at equilibrium, you're going to have a lot more products than you are reactants, than you have reactants. Okay, and that's it. So thank you for watching, and you can send me a message with any follow-up questions you have.